Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.19, crazy optimization, new API, and even some cooperation. Coming up! So let's take a look at the notes that Linus left us. So for Linux 6.19 there was no big surprise in the last week, which is great to see. And we also know that, of course, 6.19 had an RC8, it had one more release candidate. This is because an extra week of testing helps a lot, especially whenever we're in the holidays where maybe the testing is not as sharp as it should normally be. Now, another good news that we have is that next release will be called 7.0. So this is a big thing. Now, not going to talk about that because today we're focusing on 6.19 and let's get into it. So let's get into the first feature change of the day, which is the DRM Color Pipeline API. Now this is one of the biggest changes that we've seen on the graphics side of the kernel, so let's actually take the time to see all of the steps that are needed in order to draw something on screen. So to draw something, we need the hardware, of course, we need the Direct Rendering Manager, DRM. That's the code inside of the kernel that manages displays and GPUs. They're separated in two main sections. So you have the shared code and you have the vendor-specific code. So the code for each GPU, for each screens. To be able to fully take advantage of the GPU vendor-specific code inside of DRM, we need the user space driver. So the user space driver works with the vendor-specific code in order to get full usage of the GPU. So inside of DRM, it pretty much enables the GPU and pass along control to the user space driver that then will implement things like OpenGL, Vulkan, and all of these different tools that allows the GPU to be fully utilized. Now, both of them together cannot really be used for graphics because that would mean that we need to recompile every program for each specific drivers. That would be insane. So we use something called a display server. So the display server, what it does is it provides a standardized way for programs to speak to the rest of the system and get their things displayed. So X, Wayland, they have that standard that can be used in order to send an image to the screen. Now, X and Wayland themselves don't actually do a lot of the heavy lifting when it comes to processing the image. That's done by the compositor. So the compositor is that kind of hidden part that will go and set the rules for how the colors should be mixed, set the rules for how your windows should look, set the rules for how to process every frame. So when you think of a compositor, I want you to think a lot like a press. So right now, what the compositor does is it takes the element it wants to show, lays them flat, flatten it into an image, send it to be displayed. That's simple. Now, the compositor is almost always in play. The only place where it won't really, be enabled would be like playing a game in full screen. Normally, the compositor will disable itself, which is also why it can bring some performance gain if ever you're a gamer. But 99% of time, compositor will be there flattening your frame. Now, this is where the issues start. Let's think about modern screen for a moment. Modern screen actually have way more capabilities than we give them credit for. They have optimized circuit to process and blend colors. They have optimized circuit for a bunch of things that we currently do in the compositor. And also, if they're HDR compatible, they could have some greater capability in terms of color, in terms of depth of brightness, that we may not be able to fully take if the compositor is not able to detect that your screen has these capabilities, and if the compositor is not able to flatten an image in the standard format that the HDR screen requires. So here we're talking about a system where, because the compositor is too far away from the hardware, we're unable to first get the circuitry on the screen to help us, but not only that, we're often unable to actually implement the standard that the screen is expecting, thus leaving ourselves with an unused feature on our screen. So how do we fix that? Well, solution here is the new DRM Color Pipeline API. So to understand how it works, we need to understand the new DRM Color Operation, Color OP. So these operations are chained together in a list. Now this big list will be used on different parts of a frame. So just think about these operations like mixing colors, setting the brightness, telling the screen how we want each part of the frame to be processed. So these individual operations are all handled by either the screen's hardware or the vendor-specific DRM code. So at initialization, the compositor will test multiple lists of operations, and it will be able to see which one is compatible with the screen hardware and the vendor-specific DRM code. So that way, it allows it to use the most complete one. So this allows not only the processing of the frame to be standardized, because we now use these DRM color operations that are standardized, so we can now remove the code that is inside of the compositor that was there to process a bunch of things that it never should have had to process in the first place. But not only that, but it allows us to now be HDR compatible in a way easier manner, because we don't have to make a whole big part of code for HDR compatibility. We just have to make a list of DRM color operation that we know will work for an HDR frame. So there's also another gain that we have, which is the fact that the program will also be able to set its own rule. So think about an image editor or a video editor. It might need some specific processing in order to display the correct colors. So in that situation, the compositor will be able to act as a pass-through and let the image editor specify what type of processing it wants, unbothered from any other processing from the compositor. So this actually allows to simplify the job of everybody. The compositor doesn't have to know about hardware anymore. The DRM folks, they just have to implement the color operations. And we now have a way to make sure that every screen and every GPU can be optimized for these operations, so we won't have that situation where HDR is not only reliant on a specific screen, but a specific GPU on a specific driver, on a specific kernel version, on a specific compositor. That world is now being fixed. So all of that said, this is great news, but for now, not all DRM drivers have the capability to use the pipeline. For now, only AMD GPU and the generic virtual KMS driver, VKMS, have implemented it. And on the compositor front, it's not all compositors, of course. We have Valve's GameScope, we have KDE Kwin, and we have Wayland's Weston implementation that are all being worked on, but I'll keep you updated on what comes next. So let's get into the second feature change of the day, which is the removal of speculation barriers from the scoped user access code. Now, some operation requires the kernel to use pointers that have been provided by the user space. So these pointers are deemed unsafe and they require to be tested by the CPU. Even if the CPU is capable of knowing if an address is accessible by the user space, the speculation doesn't, which means that we need to prevent the speculation from running a malicious pointer. Now let's just take a moment to remember what speculation is. So speculation is the ability for your CPU to fetch instructions before they're actually needed. For example, if you have a jump instruction with a malicious address, we might leak kernel memory. So speculation hardware will essentially just guess an address, and this guess can be poisoned. So the solution to that is usually barriers, speculation barriers. They will prevent speculation from fetching any address, but it's at the cost of slowing down execution, because you're essentially telling the CPU, remove your optimization for a moment because we need to run some important things. Now, this release presents a new solution, but to understand the solution, we need to understand how the kernel actually organizes memory. So when starting a program, we grant each program with their own virtual address space. Now, this virtual address space is divided in multiple sections. The lower half is given to the user space, or at least part of that lower half, and part of the upper half is reserved for the kernel. Now, it's very important that we understand that they are separate in the upper and the lower half, because this means that we can just look at the most important bit of an address in order to know if the address is valid or not, because it will tell us if it's part of the kernel or not. So you might be tempted to just check that most important bit, right? To just use an if, but ifs use branching, if introduce branching, and in critical code, this is not what we want. So how do we make a logical and mathematical solution to this problem in as few instructions as possible? It turns out that there is a magical solution to this, and we're going to do it in x86 64 assembly. I'm going to shrink it down as if we're talking about 8-bit, but of course, it scales to pretty much all architectures. So let's start with an address that we know is wrong because it starts with a 1, but let's just do the mathematical proof to understand how the system actually does it. So the first instruction that we will use is SAR, the Shift Arithmetic Right. Now you might understand two words there. So shift and right, we understand what a shift is, right? We just push to the right all the bits. Now the arithmetic shift is a different kind of shift that assumes that we're talking about dividing a number, but not only any number, a number with a sign. So what that means is that we will keep the 1 if we start the number with a 1. Because if we're dividing a negative number, keeping the 1 actually makes sure that, well, we keep the sign. So in our case, doing this 7 times, or the number of bit in the architecture minus 1, will actually make sure that we only have 1. Now the next instruction that we use is the shift logical right. Shift logical right is the shift that we know and love. It only pushes all the bits to the right and it produces 0 where there used to be bits. So here we do it 1 time, so this allows us to produce a 0 at the very start of the address. So now we do a NOT instruction on that same address. NOT, what it does is it flips each bit. So the first bit becomes a 1, all of the other bits become zeros. Now this new address that we've created, we are going to use an AND in order to compare it with the original address. So what does this do for us? It actually only enables it to go into the middle of our address space. Now note an important thing here. We are inside of the kernel space, so the CPU will give us an error, but we don't have a specific address. The address part that speculation might abuse in order to get information has been removed. We just throw it to a place that is empty and without useful information. So with that, we have essentially removed the dangerous part of the address, and it can just be sent to the hardware to be processed, and it will still give us an error because it was a wrong address. Now let's just pass the same instruction, but for an address that is a correct address. So let's start with this address. We know that it's correct because it starts with a 0. But how does the hardware know that, right? So we need to get the hardware to understand that. Let's do the same shift arithmetic right 7 times. It will print full of zeros. So remember, last time it was full of 1, now it's full of zeros because we're starting with a 0. Now we do a shift logical right, so we put another 0 shifting to the right. Now again, that doesn't change much for us because we were already full of zeros. Then we do a NOT, so we invert all of the bits. We end up full of 1s. And after that, we use AND to compare the two. So what this essentially gives us is the exact same address as we had in the start. And this is because one started with a 1, the other one started with a 0. So we were able to use standard operations in order to clean the address. So this is not only faster, but it can be applied to every architecture. So those commands are so simple and they can often even be combined, right? The NOT operation and the AND, I know that on PowerPC can actually be combined, and I'm sure that I'm missing on most architectures how we could do it even faster than this. So this is a fast way to check the address using logic, using arithmetic, and to be able to do so without disabling the optimization of the CPU. Because keep in mind, now all of these optimizations that would need to be disabled can stay online, can stay there to make things as fast as possible. So for now, this was implemented inside of the assembly for x86, ARM, ARM64, RISC-V, PowerPC, S390. So that brings the optimization to most architectures. So now for our third feature change of the day, we have the introduction of the new TSM Subsystem. Now we've seen in the last kernel vids that most architectures and vendors are trying to make their product more secure on the confidential computing front. So AMD SEV, Intel TVX, ARM CCA, all have different ways of making sure that a malicious host cannot get access to the data of a guest. Now, PCI Express has always been outside of that trust compute boundary of these technologies. Let's just take a moment to understand how PCIe device and secured VMs normally communicate. For a secured VM, the memory of that VM is encrypted. This removes the ability to ask a PCIe device to read the VM's memory directly through DMA. This forces us to use a software I/O virtualization of the PCIe device. So the host will supply the VM with a shared buffer that will then be used with the PCIe device. This is slow and untrusted. In the event that the PCIe device, say a GPU or an accelerator, doesn't have encryption or decryption capabilities, it would force us to leak the information that we send to the buffer, the information that we want to process. In any other circumstances, we would assume that each vendor would create their own solution to this problem. But they did not. PCIe 7.0, released in June 2025, renewed the commitment to a universal solution. So let's get into it. The release brings multiple agreed-upon soup of acronyms. So we have the Integrity and Data Encryption, IDE. It's akin to TCP or an SSH tunnel. It sets the rule for a tunnel of secured communication between the PCIe device and the secured part of the CPU. We also have the Component Measurement and Authentication, CMA SPDM. It is an extension of the Secured Protocol and Data Model that sets the rules for safer communication with a PCIe device. And we also have the Data Object Exchange, so DOE. It's a method of packaging the communication sent to and from the PCIe device. Now let's see in practice how these concepts are implemented. So let's take a VM secured by a trusted execution environment, a TEE. Now, when we talk about TEE, we're talking about the secured part of the CPU that manages the VM. So Intel TDX, AMD SEV, they both do it in different ways, but they essentially have some part, either a secured mode on the core or a separate core that is able to manage the VMs. Now, that TEE, upon detecting the compatible hardware, will make it available to the VM. No permission or access is given to that PCIe device without the VM's approval. The VM can then request to the TEE to get access to a function of the PCIe device. So the TEE will then proceed to create an IDE connection with the PCIe device, encrypting its communication and allowing the VM access to the function. Subsequent transfer would be done using the CMA SPDM standard through the DOE format. This solves three fundamental issues with PCIe communications when it comes to confidential VMs. First, the communication to the PCIe is now hidden from the host. Second, the communication is encrypted. And third, we do not require a buffer for communication between the PCIe device and the VM. PCIe 7.0 also allows, with the VM's authorization, DMA operations directly to the VM's memory, increasing performance. This standard also outlines how a PCIe device should be divided in functions accessible by a TEE device interface, a TDI. So let's think about a 4-port network card. Each port is a function and is linked to a TDI. A VM may grant the TDI DMA access to its memory or send packets directly through the card. These communications are all encrypted under the IDE connection away from the host. The TEE, along with the TDI, ensures that one VM cannot interfere with another. Now, the skeptics among you might just say, what's the point of all of this if the host use a fake PCIe device? Well, the standard got you covered. So upon connection to a TDI, the TDI will transfer a signed version of their internal measurement, firmware version, and other hardware information. So this signature can be verified against the vendor-supplied certificate, and the measurement can be tested to confirm that the hardware wasn't altered. Now, this ensures full confidentiality while relying only on the maker of your hardware. Now, let's get back to the kernel because it feels like we're way outside of it right now. So a new subsystem is born, the PCI Trusted Execution Environment Security Manager, TSM. Now, the code handling the IDE connection and the framework for initiating secured connection was added to the kernel. For this release, only the AMD SEVTIO, Trusted IO implementation was included. But Intel TDX Connect and ARM CCA are currently waiting in the new TSM tree. Now, there's still a long way to go. The devs have given us a maturity map, but we'll see where it goes. I'll keep you updated. It seems that every kernel, we see more and more crazy feature that ensures confidentiality on the VM world. And this is pretty much the last bastion. And I'm just very happy to see that for something as important as PCIe, all the makers of hardware could just come together in a universal solution, right? Because the fear is that you would need an Intel card in order to run an Intel VM. You would need an AMD card in order to run an AMD VM. But as of now, as of my reading of the PCI 7 standard, it looks like we have something that is universal, that we have something that should work on every version as long as we apply the standards that were outlined there. And to be clear, these standards already in pieces of or in whole already existed. It's just cool to see the commitment to be back on the table where everybody agrees that this is the direction we should go in. So now let's go to the architecture-specific change. x86 Intel now has the LASS feature. So the Intel Linear Address Space Separation is an hardware feature that defends against side channel attacks. So when fetching an address, the CPU will do what we call a page walk. This page walk will happen whether or not you have the permission to read the underlying address. This can take more or less time depending on what is the memory used for or if the memory is cached. So as we know, in a 64-bit system, the kernel space will be in the upper half of the virtual address space. So when taking advantage of this fact, a CPU with LASS enable will refuse to let you do the page walk on a memory address that is in the upper half of your memory. This is, of course, if you are doing so while in user mode. Now, this prevents an attacker from getting timing information that might leak the underlying use of the memory. So these kind of attacks are seemingly getting more and more standard, so this just adds another layer of protection, so it's good to see. Now let's go on AMD side, where we have the AMD Smart Data Cache Injection, SDCI, that has been added to the kernel. Now, normally, if you wanted to get data from a PCIe device to the L3 cache of your CPU, you would have first put it into RAM and then get it to the L3. Now, the new SDCI feature from AMD allows us to get that data from the PCIe without copying it into RAM, saving a little bit of bandwidth. Now, of course, this is not a feature that we expect to be used by general users, but in some very optimized cases, this can help. So now let's go to ARM64, where we now have the ARM MPAM support. So MPAM stands for Memory System Resource Partitioning and Monitoring. It is a feature since ARM v8.4 for managing shared resources like the CPU cache, memory bandwidth, and other resources. So MPAM is intended to help the partition and monitoring of the ARM64 servers with multi-user virtual machine. This should help ensure that no single user disproportionately utilize too many system resources. Now let's go to Long Arch, where, well, they have some pretty big change. So we have a beginning for the implementation of Long Arch 32. Yes, Long Arch has always been a 64-bit architecture, but the work to implement a 32-bit version has begun. Now, the GCC compiler code for the new LA32 application binary interface, the new ABI, is currently being reviewed. So there is two versions of this new architecture that will exist. There's the LA32R, which is a restricted version, and there is the LA32 or LA32S, which is a complete version. Now, for now, this cannot really be compiled. There's more work that needs to be done, more fix to some driver before the implementation can be fully compiled. Not only that, but it also needs to go through the whole process with the GCC side. But this might seem a little bit counterintuitive, right? Why would we want to go back in the bit count? But this makes sense whenever we're talking about smaller things, Internet of Things device, and these kind of things that don't really need all the processing power that we're throwing at them. So in these cases, having a lower bit count using less memory is actually a big advantage on the price. And when we think about Long Arch, which is a Chinese architecture, this makes more and more sense to why they would need this. Now, That's all for Long Arch, and let's just go to RISC-V, where we have hotplug parallel support. Now, most architecture like x86 and MIPS have the capability to bring secondary cores online asynchronously with hotplug parallel support. So RISC-V was close to having this support, but it missed a few key ingredients. Now, I'm not going to talk about these ingredients specifically because we would be there for another hour, but let's just chalk it up to certified unit Anup Patel from Ventana Micro, a Qualcomm subsidiary, fixed these missing features and enabled hotplug parallel on RISC-V. So now it is faster for the enabling of secondary cores within an SoC. Now let's talk about ZigBop, which is an operation that we've talked about in the past. It's an instruction that allows to prefetch some information, so to put something in a cache before it's actually needed. So it's now available to the user space. So before it was only implemented in the kernel, and now we have access to it elsewhere. So now let's go into the file system change and start with ext4, which brings some more optimization to the online defragmentation process by leveraging folios rather than individual buffer heads. So of course this helps this defrag process, which is good to hear, but the bigger news that I want to talk about today is the support for block size bigger than kernel page size. So we've talked about this already a little bit because it's been added around to a lot of file system. We've seen support for it on XFS 6.12 at the same time that VFS actually allowed this feature to exist. And last release, we saw it in BTRFS in a more limited way because it's an experimental feature. But there's two main reasons why we want this feature. It's first of all for performance. Scaling up the block size can yield a surprising amount of gain in some benchmark, and the file system size. So the block size in most file system is the unit that will actually set the maximum size of the file system. So for example, on a 32-bit machine, an ext4 with 4 kilobyte block size will be up to 16 terabyte, while an ext4 with 64 kilobytes block size will be up to 256 terabytes. So you can see how these the changing of the block size can affect a lot how you're going to lay out your infrastructure when you were talking about these big data servers, these big servers that chalk up a lot of data. So boosting that block size, better performance, because of course most of the time when we read something, we're not expecting to read something that's 4 kilobyte in size, right? We're expecting way bigger than that. So boosting that actually gives us better performance. Now I want to dip a little bit into NTFS, which now supports the pre-1970s timestamp. Now, we know that Unix time starts on January 1st, 1970, but NTFS, of course, was not made for Unix time. So it was possible for a valid NTFS file to have a timestamp from earlier than that limit, but of course the internal code couldn't manage these timestamp. So it was rewritten to allow for negative integers, thus pre-1970s timestamp. So it means that now we won't just, of course, cause some errors if ever we see a pre-1970s timestamp. Now I also want to touch base on HFS. Not a lot to say, but we still have some support. We've been talking about it for the last 2 releases, and we still have corruption fixes, cleanups, more internal tests. It's good to see that HFS is alive and well, especially when the talk about it 2 releases ago, well, we could say 3 releases ago, was to literally remove it from the kernel. So we can see how we get from a situation where we're supposed to remove something to it just works well. We just need the manpower, which is the big issue, right? It's hard to have all the maintainers needed to process everything, to maintain everything that's needed for a file system to be up to date. Now, a block feature that I want to talk about is the full per CPU BIO caching that is now the default. Let's split a little bit of this in order to understand it. So let's start with what BIO is. BIO stands for block IO, so it's a structure, struct BIO, that is used to send information to a block device. So it contains a few fields. It contains BI next to list over multiple BIOs. We also have BI bdev, which points to a block device, and we also have BIO vec, which is a list of struct BIO vec, which themselves contain the information about the physical page we should take or put the data to or from. When talking about BIO, we need to keep in mind that the memory address used will be physical address. The BIO is meant to be used with DMA, which will allow us to get data from the place it currently is in memory to the disk and back without copying it to a buffer. So now let's address the per CPU caching part. So as we know from sheaves that were added last release, 6.18, the slab allocator can be slow for some critical context. The way the CPU will allocate memory for a BIO is by requesting an object from slab, and this often made slab the limited factor in BIO performance. So the solution to this was to look into the list of already generated BIO from this CPU, and if one of them was free, it would be used to fulfill the new BIO. Now, this per CPU caching saved the call to slab, but was still limited to some specific situation. This is because if the operation could be interrupted, it could result in a big mess, as the simplicity of this cache, which is nothing more than a linked list, did not protect against interruptions. So this patch removes the possibility of these interruptions across the board, thus allowing us to enable this cache for all BIO operation. So the benchmark currently show a small gain in performance with little to no regression, which is great to see. Now, last release, we've talked a little bit about the cryptography side of things, where we add the two-way interleaved SHA-256 hashing support that was added to the crypto library. Now, we also predicted that it would be applied to DM Verity, which it now is. So DM Verity is a device mapper that provides encryption at the block device level. So it now uses the crypto library included in the kernel, so it enjoys all of its optimization. So remember the 2x performance gain. And of course, it reduces the amounts of code that needs to be maintained. So it's a great thing to see. Now, along with that, of course, let's talk a little bit about crypto, and especially about Eric, god of cryptography optimization, bigger, that brought us a new batch of patches. And it's the same guy that did the DM Verity patch, of course, but we won't talk about that. So we have AES GCM that got a 74% performance boost on AMD Zen 3 CPUs and a lot of other CPUs along the way. So this optimization was achieved by implementing the instruction from AVX2, which are sufficient for the AES GCM, which can run on a 256-bit register. The already existing AVX 512 implementation was also made a little bit more efficient when it comes to having bigger amounts of data. So Eric had already optimized AES GCM for CPUs without any AVX in 6.11, so this makes AES GCM pretty much complete here. So whatever optimization your CPU has to be able to process these things faster, it will be able to use it. If it's a little bit more limited like AVX2, it will be able to. If it's a complete AVX 512, it will be able to as well. So all of these optimization are always available for you to use if your CPU is able to. Now let's go into the VM change, where AMD's X2 AVIC, the implementation of the Advanced Programmable Interrupt Controller APIC for VMs. So here, just to be clear, we're not talking about Secure AVIC, which is the thing that we talked about last release. That is the encrypted version of the same thing. We're just talking about the generic implementation of it. So X2 AVIC now supports up to 4096 vCPUs instead of only 512. So now it can use a feature bit, X2 AVIC EXT, that allows it to go further. Is it useful for anyone? I guess they have some big CPUs or a big need for VM somewhere. It just seems like a crazy amount of CPU cores, right? 4,000 cores. God. We also have the overall of the TDX code to address systemic races where KVM, acting on the behalf of the user space, could trigger lock contention in the TDX module. So it's a good thing to see that this was patched, but I won't go into detail. I feel like I'm so far from understanding it, it's not even funny. We also have a big addition in the form of Luo, so the live update orchestra that has been added to the kernel. So Luo builds on kexec, which is the tool that allows the kernel to pass control to another kernel, allowing updates without a full reboot. So kexec normally requires the device you use to still go through a reset process, and the data you have in memory would usually be lost in the transition. Luo gives the administrators a way to preserve the state of the device and memory region that can then be reclaimed by a new kernel. This will be used in the context of virtual machine hosts that need to keep the downtime as low as possible. So I just want you to have an image in your mind right now that we are literally able to do some magic there, right? We are able to go with the little drape on the table, just slam it down and everything stays on it. That's pretty much where we are in terms of updating the kernel, so making sure that we shut down kernel A, put another one, and keep everything running as it should. Now, keep everything running is a little bit of a gross oversimplification, but we don't need to reload a bunch of things from some hard drive somewhere or some other thing hidden somewhere. We can now orchestrate it using Luo. Now let's dip a little bit into the GPU and audio change, where the Nuvo driver now supports larger page size and compression. So here, of course, we're talking about the DRM side driver for NVIDIA, the open source Nuvo driver. Now, to understand why this is even important, let's just go into how things actually work for the requirements for a driver. So it is a requirement by Vulkan that the user space be directly responsible for the management of the VRAM. So this concept is actually called User Virtual Memory Management, UVMM. And it was implemented in the kernel as vmbind, which is a method that allows the user space to directly map some memory to the VRAM. Now, before this release, the Nuvo driver could only handle the same page size as the kernel size, so most likely 4 kilobyte, at least on x86. So this is an issue, right? Because we want to have the biggest page size, especially in a GPU context, because a GPU does not have the same sophisticated circuitry that allows the CPU to efficiently page walk. So our CPU, very fast at looking through different pages, GPU, not as much, so having bigger pages allows better performance. Now, not only that, but having access to bigger page size on the GPU actually allows us to compress them, because NVIDIA's GPUs don't allow compression if the page size is not 64 kilobyte or bigger. So this means that all across the board, through this update, we now have better performance for NVIDIA GPUs using the Nuvo driver. Now let's dip a little bit into Intel Nova Lake, which is something that will be released late 2026. We now have audio support that's enabled, along with the Z3P integrated graphic in these CPUs getting enabled as well. Now let's talk a little bit about network change, where a busy lock at a transfer queuing layer was replaced by a lockless list. Now this patch yielded a 4x improvement in heavy transfer workload. I just want to read the merge request so that you get how insane this is. Sending twice the number of packets per second for half the CPU cycles. Good news, guys. Good news. So now let's get into the other change, more precisely the subsystem for Memory Management Concurrency ID, MMCID, and Restartable Sequences, RSEQ, that has had a major rewrite. Now, kernel legend Thomas Gleixner took the task, and his work resulted in a major performance gain. So let's just start by understanding what MMCID and RSEQ even are. So it is common for a program to require a per CPU data structure. So what we mean by that is some kind of data, some chunk of data that should be accessible and loaded to only one CPU. So that makes sense because sometime if we would have some shared data structure, it would actually slow things down because we would need a lock across it. But here, if we have a data structure for one core, things can be swift. So faster transaction, lower contention in critical code. The one way to create that per CPU data structure is to create one per core. But in the context of a CPU with a large core count, this can be a very bad idea, right? If you have 200 cores and you only need 5 cores to do that specific thing, loading it across the machine is a huge waste of memory. So the better solution is to use MMCID. So MMCID allows you to set a number of concurrent CIDs that will then be used with said data structure. So whenever a thread requires a CID, it would take a CID from a pre-generated array. Then once the thread goes to sleep, the CID is not instantaneously freed from the core, so this allows the thread to quickly wake up if needed. Now, in the case where that core is used and the CIE array is empty, it would then be freed from the original core and sent to a new one. So the MMCID also plays into NUMA, so the hardware information that allows us to know how close a core is to another, and allows some optimization there as well. So we kind of fixes the two issue, right? We don't have to have that much data structures that are unused. We only set the number that we will use at a maximum, and then we can go pick from that array. And if we use some kind of optimized scheduler, we can make sure that our process actually wakes up on the right core, making things even faster. So MMCID is more of a kernel space concept. To take advantage of it, the user will use what we call the restartable sequences, so the RSEQ. The RSEQ is used with great result with databases, and the rewrite actually showed around a 14% performance gain. That's very good. I also want to give a quick word to printk, which got a 20x speed up in some circumstances. So printk is the command used to send text to the console. It worked by granting a lock to the core that was currently using the console and waiting on said core to release the lock. This could result in large delays in the release of the lock in real-time kernels. Now, the solution was to change the internal code of printk to offer a one-line print solution that would set and release the lock. This removes the contention, and in the example of the Pocket Beagle 2 used for testing, went from a 145-second boot time to 7 seconds. So we're talking 2 minutes to 7 seconds. So we need to keep in mind here that this optimization is there mainly for real-time kernel, because at boot time, your real-time kernel will only do whatever the user space is asking it to do and whatever the kernel space explicitly need to complete a task from the user space. So we would be in a situation where the releasing of the lock would be secondary to whatever is going on the user space, but that's kind of a ridiculous thing because releasing the lock should really be part of printk, right? You're done printing, then you should probably release the lock at that time and not wait on it. So great work. I'm not sure that it's going to change much for many people, but I guess if you're using low performance hardware on a real-time kernel, good for you. Now, I also want to do some quick shoutouts for some hardware. So we have initial support, and when I say initial, very basic support for the 10's Torrent Black Hole SoC. So that SoC is made of 4 RISC-V CPU tiles that are themselves made of 4 Sci5 X280 cores. That means a total of 16 cores. So it's good for running some local AI. And as you can see, it's meant as an extension card, right? So you have multiple models that exist. You have the P100A, that's at 28 gigs of RAM, retails around $1,000 USD, and you have the Black Hole P150A, which is 32 gigs of RAM and 4 high-speed port, which is currently at $1,400 USD. Now, talking about support, we also have Black Sesame Technology C1200 support. It's an automotive SoC that's ARM64 based. So it's made by a Chinese company that has made some hardware in the last 9 years, but nothing from Linux, nothing for Linux. So good to see them. The Black Sesame's C1236 is promoted as China's first single SoC for pilot navigation smart driving. And the last that we're going to talk about is the support for the Star5 Vision 5 2 Lite RISC board. So this should be the cheapest board with RISC-V core on the market. Still, this is not a Raspberry Pi killer. The performance per dollar is and will be for a long time with ARM. But if you want to get yourself on cheap RISC-V cores, that's pretty much the way to do it. Although, from what I've noticed, the lowest prices have come up a lot, right? We're not at the same place that we were even a couple of months ago. So keep that in mind, but if you want some RISC-V, that's the way to do it.